All right, so I think we should proceed. So duality is a concept that has been around for a rather long time. And historically, perhaps, so of course, these formulas, such as Poisson summation formulas, they effectively come from 19th century. But at the time, nobody was really thinking in terms of duality and why it would be useful for duality. But in some sense, the first actual transformation, duality transformation, explicit duality transformation, appeared in 1941. And it appeared in the context of the Ising model in lattice statistical mechanics. Now, this example of duality, and it's known as Kramers-Vanier duality by names of people who discovered it. And it's actually quite important. So I won't say much about it, but nonetheless, I think it's relatively important. So you model a system of gas, for example, liquid, solid state, with spins and a lattice. So you have a square lattice, for example. The form of lattice doesn't really matter much, but suppose you have spins as at each side of a lattice, and then you write down the Hamiltonian. So the full Hamiltonian H as an operator with some coupling J will be the sum over, for example, nearest neighbor interactions. If you don't want a long-range order in your system to consider it, you just consider that each spin interacts with its immediate neighbor. So this is a sum over nearest neighbor I and J of a spin operator, which is a Pauli matrix sigma. So this will be the Hamiltonian. And this is actually known as the quantum Heisenberg model, so this thing, which is fairly complicated. So each sigma is a matrix, it's a Pauli matrix, so it's already quite complicated. So this is quantum Heisenberg. Quantum Heisenberg. But you can simplify it, and instead of these sigmas, you can just introduce scalars. So to simplify it, instead of a matrix, you just take a scalar, which takes two values, 1 and -1. So Si, Sj, and each Si could be plus or minus 1. And again, sum over nearest neighbor interactions. And this Hamiltonian is known as the Ising model, although apparently it was suggested to Ising by his advisor Lenz, and Ising solved the one-dimensional model. It's Ising, not Ising. The guy was German, so please. Let me not comment further on this. But yeah, so Ising. So Ising model is enormously popular in lattice statistical physics. It can be considered in any number of dimensions, 1, 2, 3, 4, and so on, right? And famously, in d = 1, it doesn't have a phase transition. So Ising, when he solved this problem proposed by Lenz, he concluded that, well, there is no phase transition in one dimension, therefore, in any other dimension, we don't expect any phase transition, case closed. But that was an example of the dramatic strategic mistake, because in d = 2, as was shown later by Anzager, who produced an exact solution in 1944, this actually produces there is a phase transition, and so on. So this is a very popular model in various dimensions. What is important for us is that in 1941, 3 years before Anzager solved the model, Kramers and Vanier managed to rewrite this Hamiltonian or partition function, right? So we are interested in writing down the partition function. So let me just write it. Z equal to trace e to the minus beta h, and in this case it will be just sum over all si's, and each si takes values of plus minus 1, e to the k, and here you have Hamiltonian ij si as j, so this is deceivingly simple, and k is just a notation. It's beta times the coupling strength j. So what Kramers and Vanier managed to do, they rewrote, so this is z of k z of k. And we managed to change variables explicitly in this model and rewrite this in the form c of k star, z star of k star, where z of k star is sum over other variables, let me call them s star I, also taking values plus minus 1, e to the k star sum over nearest neighbor interactions, nearest neighbors, si star, sj star. In other words, this z is also z of an Ising model, but Ising model with different variables and different k, which is now called k star. So what are these s stars? So the s stars, so the original s's were spins or kind of simplified spins on the at the corners of these squares everywhere. And then s stars are also variables of the same type, but they live on a so-called dual lattice. So the centers of the dual lattice will be at the centers of these squares. So I hope it's visible. So you sort of, in the center of each square, you put another node, and then you connect them. So the square of the dual lattice will sort of encircle the vertex of the original lattice, and so on, right? So this lattice is infinite. So this is our lattice with spins. So here we have spins as star I. All right, but otherwise it's the same type of lattice, and you can write down the same type of Ising model now on the dual lattice. And the statement is that original z is this new z star of the Ising model in the dual lattice up to some coefficient which is known explicitly, but it's kind of irrelevant. So and k star, the relationship between k star and k is the following. So hyperbolic tangent of k, or in the symmetric form, you can write this as sinh of 2k times sinh of 2k star equal to 1. All right. Now, we don't have time to discuss how one does the change of variables and goes from here to here. But if you are interested in this, please read the appropriate entry in my reference list. And the appropriate entry is a wonderful review by a character named Savit. It's fairly old, in 1980s, it's Review Modern Physics. But it tells you in great detail of how to do this transformation and many, many other things, because this duality exists for other dimensions, for other models, and so on and so forth. It's a big machinery which originated in 1941, and by now it's very well established and known. It's a very interesting subject, but this is an example of how change of variables can be done explicitly. So there are formulas which tell you how to express S stars via S and vice versa, explicitly. In fact, this can be understood later in 1980s. This was understood as part of a harmonic analysis on groups, on abelian groups. All right, so I won't say more about Kramers-Vanier duality, but again, I recommend you sort of looking in the appropriate literature. The only important comment on this is the following, that this is also weak-strong duality. Weak-strong duality, which is obvious from the relationship between the coupling constant in two partition functions, right? So k and k star, you can plot them. You can plot k star versus k, right? And the plot will go like this. So the moral of the story is that if you're asked to compute something in Ising model at large value of coupling k, you have no idea how to do it perturbatively because you don't have a small parameter. You use duality. You just rewrite your z in this form with k star, and if k is large, right, somewhere here, then the value of k star is small and you can use perturbation theory. That's the main idea. All right, so, and just as a passing remark, Kramers and Vanier, so if you assume that there is only one phase transition in two-dimensional Ising model, which we assumed, then it means that there is a unique value of k at which this transition happens. So this value of k must be the same as value of k star, so because it's also Ising model, right? So if there is one phase transition, then it happens at unique value of k, which is the same as k star, and then the condition for phase transition is sinh of 2k critical squared is equal to 1. And this gives you the prediction for k critical, which happens to be minus 1/2 log of square root of 2 minus 1, which is approximately 0.4407. This was a prediction of a critical exponent by Kramers and Vanier in 1941. And then Anzager got his solution 3 years later. He confirmed that indeed there is a phase transition, and indeed the critical value of the coupling was exactly this. So fine. So this is all about examples of duality. And now let's go to string theory. Before that, are there any questions about this part? Yes?
Are phase transitions usually expected in the transition between the two duals?
You see, there is no transition between duals. The dual is just, it's the same Z, right? So it's the same system, right? It's the same system like water. I just use different dummy variables to write down the partition function. So it's not a transition to a dual, right? So you just, when you write it in different variables, and you may ask, fine, does my system have phase transitions in general as a physical system, right? Maybe it does, maybe it doesn't. That we don't know, right? So that is unknown. And how many? For example, maybe it has 5 phase transitions, right? Here we are kind of lucky because indeed there is one phase transition. Kramers and Vanier conjectured this, right? They didn't know, but Anzager showed that there is exactly one phase transition, nothing else, right? Because in principle you can say, well, so suppose phase transition happens as a function of coupling, right? And then you go from infinite coupling and you go from 0 coupling, and in between you encounter 5 phase transitions, right? So then of course you cannot do this, right? So because they will not be equal, right? So, all right, other questions? No, great. So now string theory. So string theory is yes. Probably the shortest introduction to the subject I ever gave. Let me see how it works. So string theory is a quantum theory of interacting one-dimensional and higher dimensional objects, strings and branes. So originally people started with strings, and then around 1990s it became clear that one has to introduce also these solitonic-like higher dimensional objects, which are called branes. So what do we have? We have open strings, right? So open strings. We have closed strings. And we have branes. And I described them in my popular talk. So you can think of them as fluctuating quantum hypersurfaces in 10-dimensional space-time to which open strings can be attached. So open strings can travel on the surface of the brane. The only requirement is that they're called D-branes usually. Well, there are other branes, but let me talk about D-branes. For Dirichlet. So Dirichlet condition is that the endpoint of open string must be attached to this hypersurface. So these are quantum interacting objects. Right, so quantum objects means that you have to quantize them just like you quantize a harmonic oscillator. You quantize a string, closed or open, and they have spectrum, they have they have action. So the action which describes propagation of a string is known as Nambu-Goto action. And it has this form, which I won't explain in detail. The t in front is the coefficient which has a dimension. So alpha prime has a dimension of L string squared. This is similar to the action for one particle, right, which you write down minus m integral over ds, where s is the integral over, ds is the integral over the world line. So here you have object which is one dimension higher, but the principle is the same, right? You integrate over the world line, which is swiped by the string when it propagates in space-time. Now, there is one parameter, ls, which is the length of the string. And in some sense, the beauty and attraction of string theory, and maybe one of the reasons why people, after 50 years, still don't want to abandon this enterprise, is because everything is supposed to follow from this one parameter. It's only one, there are no other parameters in the theory. So all the multitude of particles and fields and standard models and protons and God knows what is supposed to follow from geometry into the, in which the strings propagate, but there are no adjustable, no different parameters, only ls. Fine. So let's quantize. So we quantize the strings. And pretty much like you quantize harmonic oscillator, it's a little bit more involved, but in principle, it's not terribly terribly that different from this quantization. If your strings are non-interacting, right? You take ideal gas if you want a string, and take individual strings which is non-interacting, and you find the spectrum in flat space-time. And the spectrum of open string will be different from the spectrum of closed string because of different boundary conditions. Not a big surprise. So this spectrum will look like this. So in closed string, both in closed and open string, you will have the ground state, which are massless fields or massless states. And then there is an infinite tower of massive states with masses which are proportional to 1 over ls. Right? I remind you that ls is the only dimensionful parameter in the theory. There is nothing else. So, of course, so massless states, they form particular multiplets. You can write them down exactly. And these multiplets involve, in the case of closed string, they involve a symmetric tensor G mu nu. Then there is a scalar. Then there is pseudoscalar, and then there is a tensor B mu nu, and then some exotic fields, which are, well, similar to Maxwell fields, and some fermions. So, and this is a set of massless fields, which you can discover that actually these fields, they form a particular type of supergravity. Fine. Now, what about, so, okay, so you look at these fields and you ask yourself, yeah, so in the case of open string, the situation is similar. So you have massless fields, and you have infinite tower of massive states. Massive states, different from this one, but nonetheless massive. And the the states, the massless states, will contain a gauge field, and then some scalars, and then some fermions, and so on, right? So let me, okay? So the major difference between the two types of strings is that among massless states, closed string will contain a field which resembles a graviton. And indeed, you can show that this is nothing but, so this is gravitational field, G mu nu, metric tensor. Whereas open strings don't have this field, but instead they have something which resembles gauge field, A mu. So already here, on the level of this simple spectrum, you can kind of suspect that if I describe something in two languages, open and closed strings, then I have something which involves gravity and something which involves gauge fields. And if this description of the same object is equivalent, then I should be able to describe gauge fields in terms of gravity and vice versa. So if you want, this is the origin of the gauge string duality. So this is the root, if you want, of this. Fine. So what about equations of motion? So we have these states, and we also want to write down equations of motion for them. So equations of motion follow from the string theory, from principles of string theory, and I won't have time to discuss why and how. This is a rather involved subject which was developed in the 1980s, and people derived these equations of motion, and I only focus on the equations at low energies. Low energy means that energy is much less than 1 over Ls. Right? Remind you that there is only one parameter in the game. So low energy. So at low energy, you have equations of motion for these guys, for these fields, for massless states. And these equations of motion are actually quite beautiful. So I will write only one of them to show you that these equations, so I omit some terms which are of no importance for the rest of our discussion. Only nu, lambda, rho, sigma. There is some field, right? So don't worry about this. So and some other similar equations. So what I want to emphasize is that at low energy, closed string theory produces something which resembles Einstein's equations, right? Equations of general relativity. And one of the attractive features of string theory is that at low energy it reproduces what we know should happen to gravity. The gravity should obey Einstein's equations of general relativity. And it also produces a generalization of these equations, right? Because this is Einstein's equations plus some other stuff. So then sometimes people sort of accuse string theory of lack of predictions and so on. It's not entirely true, right? The string theory produces generalization of Einstein's equations with specific coefficient in front of these. Yeah, so in principle, if we were able to go and measure some physical phenomena, such as precession of the perihelion of Mercury and something like that, with a precision of the order of Planck length, right? So then we could confirm or refute the theory. So prediction is there. These corrections are extremely small, right? So there is no way to go and measure them.
Andrei,
yeah.
What about compactifications here? Does it depend also on compactifications?
Yeah. So there is also So this is all happening in 10 dimensions, which I didn't. So this is 10 dimensions. For self-consistency of the theory, we have to have 10 dimensions, and then there is a question of how to get down to 4 dimensions in order to describe our standard model and so on and so forth. I don't want to go into this because for duality, this is completely irrelevant. Right? It's relevant for considering string theory as a theory of nature. Right? So thankfully, our goal is far more modest. We just use mathematical tools in a self-consistent mathematical theory in order to produce to get our transport coefficients and so on, right? It's completely irrelevant whether or not this theory is a theory of nature.
In 4 dimensions.
Yeah. What? No. I stay in 10 all the time. Yeah. So I don't care about compactification. So that's right. So great. So we have a system of these equations. How about solutions? Well, there are solutions. I will write one of them. So the metric, so G mu, right, is a solution of this equation in 10 dimensions. And this metric is very simple. It has this form, dt squared plus dx squared plus dy squared plus dz squared. And then there is another part, h1/2 of r dr squared over f plus r squared. And here I have a metric in a 5-dimensional sphere. And h is 1 plus L to the 4th, some parameter which depends on Ls, divided by R to the 4th, and F is 1 minus R0 to the 4th over R to the 4th. This is an exact solution of this equation, low energy equations of motion. Very good. So then, it resembles a Schwarzschild solution. So this is, we come back to this in a moment. But so far, I just stress that this is an exact solution of 10-dimensional low energy closed string theory. Fine. What about open string theory? Suppose that I want to describe this solitonic-like object like a brain, right? So let me let me see how I can do it. So I can do it in two ways. So one way is using the definition, right? The definition is that I have open string which are attached to this object, attached in the sense that they are free to move along with 3 + 1 dimensional. So for simplicity, consider D-free brane. So it has 3 + 1 dimensional world volume, and the endpoints are free to move around this world volume. At low energy, this is a key word, so at low energy, at energies which are much less than 1 over Ls, excitations of these open strings will not involve all this infinite tower of massive states, right? I'm only at low energy, so I only consider massless fields, okay? Now, massless fields are gauge fields, plus some scalars and fermions, and I can write down an effective Lagrangian which describes the endpoints, the motion of endpoints on the brane. But the brane itself is nothing but the locus of those points. There is nothing else there, right? It's just, by definition, the brane is the geometrical place where these endpoints are attached and are moving around. So when you say, describe me the brane in terms of equations, in terms of the action, all I have to write is the low energy action of the massless fields, if I'm at low energy, okay? So let's do exactly this. And write down the Lagrangian, and the Lagrangian happens to be of this form. So trace 1/4, so you recognize this Lagrangian as a gauge theory Lagrangian, plus you have also terms which describe fields, are the fields, scalar fields, and they're kind of, so, okay, let me write down and I will explain. It's a commutator plus fermions. So this is at low energy. So what happens? So the theory of this low energy fields is a gauge theory. It's a gauge theory of type SUNC. So these guys are non-abelian. So trace indicates this. Right, so these are non-abelian fields, and so these are matrices, n by n matrices, all of them, right, including these scalars phi. Therefore, there is a non-trivial commutator. So this is a potential for these fields. But it's a decent gauge theory where I can do, for example, perturbative calculations, or I can do lattice calculation if I can. I mean, this is a little bit more involved because this theory happens to be supersymmetric. So it's not QCD, it's a different theory. It has a number of interesting properties. You can compute, for example, beta function of this theory, and so on and so forth. So, but again, so I stress that at low energy, there is nothing but a gauge theory of particular type, which means that gauge fields like gluons, plus some scalars, plus some fermions, and these are bosonic and fermionic degrees of freedom, relativistic, and not infinitely far from gauge theories which we usually encounter. Fine, but I'm looking at this object which has a 3 + 1 dimensional world volume. There's a symmetries of Poincare symmetry along the 3 + 1 dimensional world volume. And I have another language to describe precisely the same defect in 10-dimensional space-time. And this language is a language of closed string theory. Because if you, for a moment, if you forget about this f, let's put f to 1. Let's put r0 to 1 and f to 1. What is written here is simply a metric in a flat Minkowski space-time, right? Minus dt squared plus dx squared, dy squared, dz squared. So what is written here is a particular solution, the gravitational solution, in 10-dimensional space-time, and this solution has a flat horizon. At a flat horizon, flat meaning Minkowski horizon of this type, right? So it describes a sheet of paper, a sheet of, not paper, a sheet of some energy, I don't know. But you can think of it as a sheet of paper embedded in the 10-dimensional space-time, but this sheet is heavy. It has some tension or some mass per unit volume, and therefore it curves space-time. So you can think of the sheet, but in fact, the space-time around it is curved. So So there is some mass, and this mass curves the space-time. Okay, but again, the symmetries are the same as the symmetries of the brain. Yep.
We assume that this brain is made of massless stuff.
Yes.
But
Yes.
now you say that it curves.
Yeah, because it has energy. I mean, these fields, they are massless in the sense that the rest mass is equal to 0, but even light has energy, right? So if you, yeah. So even in the beam of light also curves space-time. It's the question of how much, but right. Great. So we have two descriptions, therefore, of this object. One description is given in terms of this Lagrangian describing open strings at low energy. And the second description, so let me draw it like this. So again, so this is a open description, open string description. All right, so there are these open strings. The energy is low, 1 over Ls. And you have a particular gauge theory, Young-Mills theory. And this Young-Mills theory, yeah, I forgot to say that in order to get group S, U, and C, you have to take NC brains together. So it's not one brain, but there is a collection of NC brains, and this means that your theory will be SU and C. And there is some coupling constant, G Young-Mills. Okay, and this is all you can say about the brains in this language. There is nothing else. You can compute corrections to this. So of course, if you take into account massive states, there will be correction to this Lagrangian, and you can write down these corrections. But if you go to very low energy, this is the only thing that remains. Now, the same object in the language of closed string theory is described by the solution which I'm just erasing now. Right? There is a gravity solution, and I will represent it in this pictorial form, right? So there is a solution. It's kind of a Schwarzschild solution, but with horizon, which is flat Minkowski space. So let me draw it like this. So what are the characteristics? So everything is in 10 dimensions. So this is E much less than not over less, 10 dimensions. All right, so here is also 10 dimensions. All right, and this is closed string theory. Great. So what are the parameters here? The parameters here are, remember we had this parameter L, capital L, which characterizes, you can think of this as a Schwarzschild radius. I mean, there is one parameter which characterizes the solution, the metric which I just erased. And also, because we are talking about string theory, the other parameters in the game are Ls, right? And then there is another parameter which I didn't talk about. It's coupling strength of strings. So if you have, so we were always talking about individual strings, but strings can interact with each other. So you can have, for example, one string and then a second string, they meet each other, right? And then something happens, and then they go their own ways, again, like this. But somewhere in the middle, yeah, sorry. It's not a terribly good picture, but yeah, so string number 1, string number 2, they interact and then they go their separate ways. But this strength of interaction is characterized by what is known as a string coupling constant GS, which is not an independent parameter in the theory. It's an expectation value of one of the fields in the theory. And therefore, I repeat, there is only one parameter Ls. There is nothing else. But it's convenient to introduce this GS, which is expectation value of some field, and just characterizes the strength. So fine. So we have one object, which is this brain, or a collection of brains. And we suspect that we have two descriptions of the same object. And we suspect that these descriptions are equivalent in the sense that they describe the same thing. So therefore, the left-hand side and right-hand side should be the same. There should be some dictionary between the language of open and closed string theory. So it's a conjecture In fact, it remains a conjecture. But this is the origin of ADS-CFT correspondence or gauge string duality. So are they equal or not? How do you tell? I mean, this was suspected around 1996 that these are two descriptions of the same object. How do you tell if they're equal? Well, how do you tell that I don't know, that there are two macroscopic objects and they are the same? You look, right? You look. When you look, it means that you are doing scattering experiment with light, right? The light comes to this object, to your eye, right? And then you compare. So in order to compare these two, you do exactly the same. You do a scattering experiment, right? You take some stuff and you scatter in this picture and in this picture. So what does it mean? You take, for example, so do scattering experiment, right? So do scattering experiments. Of course, it is a Gedanken experiments, it's a thought experiment. Right? So suppose you have description in this language, right? It's all in 10 dimensions. So you do a scattering, you send some, for example, some scalar field or gravitational field, gravitational wave, let's say, right? Some wave. From far away, you send it to object number 1, and it scatters, and you write down what is the scattering amplitude, what is the cross-section, and so on, as a function of a frequency in your apparatus, thought apparatus, Gedanken apparatus. And then you repeat it in this description, because here you can also, you know how to calculate this, right? There is some gauge theory, suppose electromagnetism or something, right? And you can send some field, you can send a gravitational wave, and the gravitational wave will interact. So this theory has energy momentum tensor, our favorite character in these lectures, right? So it has a distant Lagrangian, therefore it has a distant energy momentum tensor. And if you send some gravitational wave, for example, this gravitational wave will couple to this tensor, right? H mu will couple to T mu and do something with your theory, and you can calculate, something comes back and so on. And again, you can calculate cross-section as a function of frequency, and you can compare these calculations here and in this picture and see if they give the same result. Right, so this is how you compare two objects. So these experiments, thought experiments, were done around 1996, 1997, and I really recommend you, so if you want to kind of understand where the whole thing is coming from, read papers by Klebanov, Igor Klebanov. In particular, there is this fantastic, very short paper, extremely simple in technically. And other people, of course, did similar things, but I really, so this is the best. So it's something like 12 pages, 13 pages. And at the level of the second year and the graduate, the technical calculations are very, very simple, extremely deep. And this is one of his fantastic, kind of priceless contributions to, right? So what he showed was that sigma in both cases is the same. It's identical. So you have identical object. So then, fine. So moreover, so it's what he did was more of that. And he and other people. So it was a kind of very popular industry around 96, 97. So the scattering showed the following. So if you do the scattering, you encounter some sort of effective potential in this closed string picture. So you write down your equation in form of Schrödinger equation, there is some effective potential. And this effective potential has this interesting property. So it has at low energies, it has sharp peak, and then it goes flat. So this is all in 10 dimensions. Okay. So this region, so this is the original metric, and this region is known as the near horizon region. So all the stuff, right, all the stuff of this solution is kind of concentrated in the small region, and the rest is flat space, 10-dimensional space. And this region, if you look at the metric which I wrote earlier on the board, this region geometrically is nothing but anti-de Sitter 5-dimensional times the 5-dimensional sphere. You can convince yourself that this is so. So the moral of the story is that you identify, so this region, ADS5 crosses 5, and all excitations on this region, like strings, you identify with the Young-Mills theory, which describes in a different language your object, your brains. So this means that, fine, so this is identified with Young-Mills theory in 3+1 in 3+1 dimensions, because this is 3+1 dimensions plus the rest 10-dimensional Minkowski space, and here you have ADS5 crosses 5 plus flat 10-dimensional Minkowski space, so you identify whatever remains. So this was the origins of ADS-CFT correspondence, and in this identification you also have the following formulas. So the relationship between L, this parameter of the gravitational solution, divided by L string, was, again, quantitatively you can show that this is identified with the so-called 't Hooft-Kaplan lambda. So this is 't Hooft-Kaplan in Young-Mills theory, and GS, the string coupling constant, is identified with G squared Young-Mills divided by 4pi. So these are the first entries in this dictionary. So I won't have time to discuss why this is so, just trust me. And when they wrote equal sign there, it can be quantified by saying that the partition function of the right-hand side and the partition function of the left-hand side coincide. So Z Young-Mills, the generating functional, as we want to calculate it, in D equal 4, or 3+1, is the same as the generating functional of so-called type 2B string theory, the closed string theory, on ADS5 cross S5 of some J tilde. So of course, this by itself, it requires identification, just like in Kramer-Swanier duality. You have to provide some formulas which tells you how to relate J tilde, for example, with J, and so on. Otherwise, it's meaningless statement, right? But these formulas can be provided. So then there is another step, almost close to the end. So this, again, so this remains a conjecture. And so this is Maldacena, November 1997. Okay, based morally, if you want, on all these Gedanken experiments and so on. So many people suspected that this, Maldacena did this decisive step. So he wrote a paper, kind of spelled out this. So fine. So we have a conjecture that this is equal to that. There is only one problem. Nobody knows how to compute the full type 2B string theory on this curved space-time. At least at the time, nobody knew how to do this. And it's kind of useless. But you can take certain limits and make this equation into something very, very useful. So the limit you take is the following. So in Young-Mills side, let's take the limit of very large NC, right? So after 1970s, after 't Hooft and so on, we know that this is a useful thing in gauge theories, SU and C, to take a limit of large N. And let's take the limit of very large 't Hooft-Kaplan lambda. So what you get is the same partition function, but now in this limit. In this limit. So what happens? You have to take the same limit on the right-hand side, of course, because this is equal to that. So what happens on the right-hand side? On the right-hand side, we have these identifications here, right? And it means that taking, for example, lambda to be extremely large means that you have to take the limit in which capital L is much larger than LS. And you can also compare this L to Planck length, and this corresponds to this corresponds to taking very large NC. So what these inequalities mean? They mean that you are taking the semi-classical limit of your closed string theory. And what do you do when you have a functional integral and you take a semi-classical limit? You make a saddle point approximation of some sort, right? And the saddle point approximation here would correspond to replacing this in the first approximation to e to the minus s gravitational action, classical gravitational action of some j, plus corrections, which in principle you can compute. And this is still supposed to be equal to, a conjecture to be equal to each other. Great. So the moral of the story here is the following. So we don't know how to compute here on this side, but we certainly do know how to deal with gravitational action. Everybody can compute whatever we want, right? So the only price to pay is that we have to go to this limit. But this limit is of great interest itself. It's the limit of infinitely strong coupling in the gauge theory, right? So this is precisely what we want. We want some quantities, including transport coefficients and spectral functions and correlators and so on, in the limit where which we cannot access perturbatively. And here it is, right? We have a formula which allows us, by using the dual gravitational action, if you have a dictionary, how to compute from this side, how to identify J tilde with J and so on, it allows us to compute anything we want on the left-hand side at infinitely strong coupling, plus inverse coupling corrections. So this was a great sort of step which attracted so many people. That's why there are so many people working on this holographic conjecture, because it gives us a tool very easily to access non-perturbative domain where other methods simply cannot produce anything, especially if you're dealing with real-time processes. So let me finish. All right, so this gives you a recipe. Right, so this in particular gives you a recipe to compute, because this is generating functional of Green's function, right, of correlation functions, to compute G retarded of omega and Q. Remember, this is what we wanted in Young-Mills theory. Which one? Well, the one in question, this one, right? So that's in the limit, right? In the limit of infinite NC and infinite coupling from gravity. Okay. Perfect. So let's do the computation. And yeah, that's almost the end. So let's do this computation. Well, of course, when I say that, yeah, so you have this identification here, and it's a recipe to compute GR and so on. This hides, of course, a certain work, so it's not absolutely immediate, but it's not a terribly complicated work. It's just a technical thing which you can, if you're interested in doing this professionally. As I mentioned in the beginning, there are 7 books written on the subject, so you can go for this. So this is something, thankfully, so for people who want to work on this, it doesn't require the full knowledge of string theory, of like all the volumes of Polchinski and Green-Schwarz-Witten. So this is a fairly simple road, a fairly simple way to get to the concrete computations. So what we get? So we find from gravity side, so we wanted our G retarded, right? So remember, G retarded, xy, right, of energy momentum tensor. And here is the answer, minus pi squared n squared t to the 4th divided by 4 I omega hat minus omega hat squared plus q hat squared. I will explain in a second what hats mean. Plus omega squared hat log 2 minus 1/2 plus corrections. So in principle, this can be computed exactly for any omega and q, but but this is expansion for small omega q. Cube q hat squared omega hat, where omega hat is just a notation omega divided by 2 pi t, by Matsubara frequency, just for convenience. And q hat is the same. It's q divided by 2 pi t. T is the temperature. Great. So we remember our linear response. Linear response tells us that the change of txy is minus g retarded xy xy times h xy, right? And delta h xy was minus p times h xy, so this formula already appeared somewhere, dt h xy plus higher corrections like eta tau p. These are second order hydro, which you can also extract if necessary, plus higher derivatives. Perfect. So we have these two, right? And we have explicit expression for G retarded now, computed from first principles microscopically. All right? Explicit form. So you can just substitute this into here, delta t in this form, and read off from the comparison of these three lines. You can just read off the values of eta, p, and if you want also tau p. Well, what do we get? We get the following. So compare. So let's see. Suppose this is star and this is two stars. So compare star and two stars, and you get the following. You get pressure, which is pi squared over 8, n squared c t to the fourth. Shear viscosity, which is pi over 8, n squared c t cube. And if you want, you also can extract second order transport coefficient, which is 2 minus log 2 divided by 2 pi t, and so on. So these are values, okay? So these are values in particular theory, supersymmetric Young-Mills theory, that one, at nc going to infinity and lambda going to infinity. So of course you expect corrections to these, corrections to this, and correction to that. Okay? And finally, you can notice, so of course if you have pressure, from pressure you can easily compute the, by thermodynamics you can compute the entropy, right, by usual thermodynamic formulas. And the entropy is equal to, so let me write it here also. So the entropy density is pi squared over 2 n squared c t cube. Right, so this you can get from that. And now you notice that viscosity in relativistic theory scales as temperature cube, and entropy density scales as temperature cube. So it's pretty natural to divide one by the other, and you will get the ratio of shear viscosity to entropy density equal to, if you restore the fundamental units, then it will be this expression. So again, in limit of lambda going to infinity and c going to infinity in this particular Young-Mills theory, in particular. All right. So this is how this computation goes. Now, a few comments. We are done more or less. So this is kind of one of the examples where a transport can be computed in the non-perturbative domain. And historically, that was the first computation of transport non-perturbatively. And you can ask, okay, fine. So you got this 1 over 4 pi Great, but you know that there are corrections, so this is in the limit, right? So then there are corrections to this, right? So corrections will go in powers of 1 over lambda to some power. We know actually which power by string theory it's 3/2 and 1 over nc squared. So you may want to compute these corrections, and they have been computed, some of them. The second question is, what about this number? Is it the number, is it the value which is true only in this particular theory, which happens to be n equals 4, supersymmetric Young-Mills theory, a very special type Lagrangian I wrote for you? And surprisingly, the answer turns out to be no. This value is also the same, 1 over 4 pi, for any gauge theory with a gravity dual description in some parameter space limit. So if you have a theory which is described by, in some limit, right, for example, infinite coupling limit, by a dual gravity of any type, you don't even know explicitly what this gravity is, there is a theorem which guarantees that the value of shear viscosity to entropy density is 1 over 4 pi in this limit. Of course, corrections are not universal. Corrections are specific for specific theories. But the limit is universal. So then you look at this value at 0 coupling, right? So this is at infinite coupling. So this is a 8 over s as a function of coupling. This is a plot I was showing in a popular talk, right? So if you want, so all this suffering of 4 lectures for you, right, basically boils down to one statement that we extracted in a class of theories, we extracted a quantum of knowledge. It's very small. We know now how this thing behaves at strong coupling. This particular and other transport coefficients, how they behave at strong coupling. We don't know how in QCD the same transport coefficient behaves at strong coupling. There is no computation which allows us to do it because we don't know the string theory dual to QCD. But we know that for a very large class of gauge theories, it must be a limit which is coupling independent. And this is where duality can be of some use, and this is an example of how this knowledge is extracted. All right, thank you. I will stop here. Questions? Yes?
Is there some experimental indications for these relations?
For this value, you mean?
I saw some papers.
Yes, yeah. This became rather popular, and people tried to. Well, first of all, it became probably popular for one reason. Before this calculation was done, experiments with quark-gluon plasma used as a benchmark the perturbative QCD calculation, into which they substituted blindly the value of the coupling relevant for RIC. Of course, we knew it's not the right thing to do, right? Because you have a perturbative calculation and you stuck the coupling constant of order 1. But they thought that it will be, okay, maybe 20%, 50% off. I mean, something like happens with pressure, for example, or energy density. And it turns out that it was orders of magnitude off. Right? And then so that created some crisis around the year 2000, 2001, and people thought that actually it means that the relativistic Hydra description of the quark-gluon plasma is completely wrong, because it doesn't, the experimental data completely didn't fit this way. So, and then this calculation was done in a theory which is not QCD, but nonetheless it was the first calculation of non-perturbative, of transport in non-perturbative domain. So these phenomenologists, of course, were extremely happy to take this limit and try to get into this experimental Navier-Stokes, right? And they discovered that it worked extremely well, within a factor of 2 of the actual, right? So that by comparison to what they had before, it was. So presumably this generated a lot of interest into this subject, and people started to measure viscosity in various other experiments, including the cold atom experiments, and also which is my favorite actually. There are some groups which measure this quantity in some experiments which are classified. So these are some nuclear, so apparently these are some simulations of nuclear explosions and so on, but for some reason they also got interested in this question. Yeah, so it's curious because you don't get it explicitly, but they kind of, yeah, they tell you the result, but they don't tell how it's gotten. Yeah, so that generated this interest in experiment. Yeah.
Other questions, please.
There should be some.
I missed the point that beta divided by S minus H bar K plus there is no H bar.
H bar, no, here there was no H bar, so H bar was reinstated. All the calculations here and there were done with H bar put to 1, right? And I simply reinstated H bar just to emphasize that we are getting something. I just remind you that this, in a sense, this thing is a property of the black hole horizon, right? Because we mapped this into property of black holes. And in some sense, it's similar to Hawking, right? So Hawking had this, remember, Hawking temperature was also proportional to this H bar, right, and so on. So, and that was a property of the horizon black hole. So he considered equilibrium properties of black hole, right? So here we are talking about near equilibrium properties. So we had a black hole, if you want, and you shake it a little bit, and then but this universality that I mentioned is related to the fact that the horizon is kind of a universal. It's very difficult to. This is no Hare notion, right? So it is very difficult to have different horizons if you have a black hole solution, right? So that's why there is this universality of shear viscosity.
So, let us thank the speaker once again.